Gravistars, the enigmatic cousins of black holes. Imagine an object so indestructible, extreme, and incomprehensibly brutal that it could obliterate black holes, gravitational stars, and even cosmic soap bubbles filled with pure energy. Its shell would be crafted from the most bizarre material nature could ever allow. But what are these objects? What do they look like? Are they just a theoretical daydream? Or could they redefine our understanding of the universe forever? When massive stars die, they do so in the most dramatic way possible, a supernova. In a split second, their cores collapse under the immense pull of their own gravity. The outer layers of the star rush inward, crash against the core, and explode outward in a spectacular burst of energy, often outshining entire galaxies. Depending on the star's mass, two outcomes are possible. Either the core compresses into an ultra-dense neutron star, or it collapses into a singularity, an infinitely dense point where the laws of physics break down entirely. But there's a third, stranger possibility, a gravistar. Instead of collapsing into a singularity, the core is crushed even further, like pulverizing a rock into dust with a cosmic hydraulic press. The particles are squeezed so intensely that they transform into pure energy, creating a tiny bubble universe. As this energy bubble expands, it collides with the collapsing star around it. The unimaginable gravitational mass of the star meets the explosive force of the energy bubble, a cosmic battle between an unstoppable force and an immovable object. Trapped in this struggle, matter is forged into something entirely new, a type of material never before seen, but theoretically possible. This violent process halts abruptly, and a gravistar is born. A gravistar might resemble a cosmic soap bubble. Like black holes, they can range in size, but a typical one could have the mass of 10 suns and a diameter roughly the size of London. Its outer shell is one of the strangest phenomena in the universe, utterly dark and unimaginably cold, just a fraction of a degree above absolute zero. The shell of a gravistar is made of a substance unlike anything we know. It isn't composed of atoms. Instead, it's an entirely new type of matter, existing at the absolute edge of physical possibility. This shell is so thin that atoms seem enormous in comparison, yet it is unfathomably strong. Inside a gravistar, things get even stranger. Its interior is a perfect vacuum, devoid of atoms, particles, or even waves. It's completely empty, yet paradoxically, this emptiness is filled with the most fundamental and raw form of energy in the universe. Understanding how this is possible requires delving into the nature of nothingness itself, a concept that may hold the ultimate secrets of reality. The inside of a gravistar messes with our understanding of reality. It's not empty space. It's a form of supercondensed nothingness. What does that even mean? Let's break it down with some metaphors to make sense of what physics tells us. In the world of particles, quarks, electrons, photons, and more, nothing is truly solid. Instead, particles are like waves in an invisible ocean. On Earth, waves need water to exist, and at the smallest scales of reality, particle waves need a kind of universal fluid to ripple through. This invisible fluid is the vacuum, what we usually think of as nothingness. It's the fundamental fabric of reality, the background ocean that allows particles, and everything made of them, to exist. Even when no particles or waves are present, the vacuum is still there, brimming with energy. This vacuum fluid isn't just out in deep space. It's everywhere, even here on Earth. The room you're in right now is 99.98% vacuum. The gaps between the trillions of particles in your body, vacuum. But here's where things get weird. When a massive star collapses to form a gravistar, it's as if the universe takes a cosmic compressor and squeezes as much vacuum fluid as physics will allow into the core. This creates a form of super-dense nothingness, an unimaginable concentration of vacuum energy. To put it into perspective, the vacuum inside a gravistar contains a billion trillion times more energy per cubic centimeter than the vacuum around us. This level of compression is the absolute limit of what physics allows before the universe breaks its own rules, like it does with black holes. The supercompressed vacuum wants to expand, to return to the vast ocean it was pulled from. But it's trapped inside the Gravastars' impossibly strong shell, an indestructible prison forged at the edge of what's physically possible. The result is an eternal stalemate, the compressed vacuum trying to escape, and the shell holding it in place. It's a battle between two ultimate limits of the universe, both pushed as far as they can go without collapsing into something even stranger. To us, Gravastars look nearly identical to black holes. They're cold, dark, and incomprehensibly massive. Their intense gravity warps space and time just like black holes do, creating the same phenomena we love about them: accretion disks, light traps, and time dilation. If you were unlucky enough to fall into a Gravistar, you'd be torn apart by gravitational forces long before hitting the surface. Your remains would dissolve completely on contact with the shell, converted into pure vacuum energy inside the star. This would make the Gravistar slightly more massive and just a tiny bit larger. Gravastars challenge our understanding of the universe's limits. They're black holes' mysterious cousins, different, yet so similar that we can't distinguish them from the outside. Exploring these objects isn't just theoretical fun. It's a journey to the very edges of physics, where matter, energy, and the nature of existence itself are redefined. You might think, is this just another case of science chasing far-fetched ideas? But let's look at history. Over a century ago, black holes were proposed as a bizarre solution to Einstein's equations of gravity. For decades, they were treated as mathematical curiosities, valid on paper but too weird to exist. Few believed they could be real. Then scientists kept investigating. They found stars slingshotted by unseen giants. They watched light bending in strange ways around invisible voids. Despite their beauty, black holes come with serious issues. The concept of singularities, infinitely small, infinitely dense points, shatters the foundations of our understanding of physics. These contradictions have puzzled and frustrated scientists for decades. Gravastars offer an alternative. They avoid singularities entirely and don't seem to delete information. Instead of a mysterious point of no return, they have a physical shell of exotic matter and a super-dense vacuum core. These features solve many of the problems black holes create. But they come with their own challenges. Exotic matter, for example, is something we haven't confirmed in the real world, and the idea of a super-dense nothingness is just as mind-bending. So, how could we ever know if Gravastars are real? There's one key difference. Black holes have an event horizon, a boundary beyond which nothing escapes. Gravastars, however, have a physical shell made of actual matter. This distinction becomes important when they collide. Two objects as massive as black holes or Gravastars smashing together create gravitational waves, ripples in space-time traveling at the speed of light. You can think of these waves as cosmic music. A black hole collision would produce a sharp, deep thump, like a bass drum. Gravastars, with their physical shells, would produce echoes, like the reverberations of a gong. Scientists are actively listening for these differences in the music of the universe, but the intense gravity surrounding these objects muffles the signals, making it incredibly hard to tell them apart, like trying to distinguish two instruments playing behind a thick concrete wall. While we've made great progress, our technology isn't quite there yet. Gravastars have the potential to answer some of the deepest mysteries in physics, or they might be just another idea we eventually discard. Either way, exploring them is part of what makes science so exciting. The nature of discovery is that it's always evolving. Black holes were once dismissed as absurd, and now they're a fundamental part of our understanding of the cosmos. The same could one day be true for Gravastars, or something even stranger we haven't imagined yet. This is why we do science: to challenge what we think we know, to question the impossible, and to move closer to understanding the nature of reality itself. What we accept as truth today might be proven wrong tomorrow. And that's the beauty of it all.